we have come to the last week of this 12-week course. We have done 11 weeks of CFD, and in the process we have learnt how to solve numerically the exact equations which govern the motion of a Newtonian fluid. We have seen that while we are making approximations at several stages during the evaluation, we have the quiet confidence that we can solve these equations faithfully and expect to get a solution which would match with the exact solution pretty closely. And we also have seen in the last week's lectures how we can deal with irregular geometry using finite volume method. So all this gives us a quiet confidence in terms of the capability of a CFD. This is very well and good, but when it comes to practical flow problems, we have a number of other phenomena which erode this confidence. In many cases, we won't be able to solve the exact equations because the equations cannot be, not enough knowledge is known, not enough is known about these phenomena, or not enough is known to come up with mathematically accurate models for these phenomena, and we may not be able to solve those mathematical models which are best for the phenomena in the context of a CFD solution framework. We note that in CFD we are able to solve the scalar transport equation very well, but if we have some integral partial differential equation which for example governs the radiative transfer in a participating medium, then that kind of mathematical model is not readily amenable to CFD type of solution. There may be some other mathematical representations like Markov methods, probabilistic methods, which again may not be readily solved easily in the context of a CFD type of approach. So there are definitely mathematical models which do not lend themselves to CFD type of solution, and if we have phenomena which occur of that type, then tackling them in a CFD context is going to be difficult, and very often we have to make gross approximations. One such difficulty with regard to practical problems where we have to make significantly simplifying assumptions is the case of turbulent flow. Turbulent flow is known to everybody. I think we all have heard about what turbulence is, and we would have seen many movies talking about air turbulence and the way that passengers feel in an aircraft as the aircraft hits a pocket of turbulence. So those kind of familiarity is very much there in our conscience, and we also have the basic idea of turbulent chaotic life is one such again a connotation which is pretty accurately descriptive of the turbulent flows that very often happen in many industrial natural conditions. So we can say from a fluid mechanics point of view, turbulence is something that is quite common, and we see that every day as water flows through the pipelines and as it comes through the faucets into buckets or whatever. As we take shower, we have turbulent flow of water falling on us. So it's quite common, and at the same time it's also quite complex for us to treat mathematically. We are going to look at that particular aspect in this last week's module, starting with some idea of what turbulent flow is and why we have to take so much care about it at this stage in the CFD solution. Okay, so turbulence can be taken to be a three-dimensional unsteady viscous flow phenomenon that occurs at high Reynolds numbers. Okay, we all know about Reynolds numbers, and we all know about viscous flow, which is the default type of flow that would happen in whenever we have fluid, except in the case of inviscid flows, which are not possible in real life conditions. We have viscous flow, and when the velocity of the fluid is high, then there is a possibility of the flow becoming turbulent. This transition from laminar to turbulent can be quite marked, abrupt in certain cases. It may, in other cases, it may be quite a slow transition, gradual transition from a state of being laminar flow to a state of being fully blown turbulent flow. Okay. We know from our basic fluid mechanics lessons that if we define the Reynolds number as a characteristic velocity times characteristic length divided by the kinematic viscosity of the fluid, then for pipe flow, Reynolds number, critical Reynolds number at which this transition takes place is of the order of 2000, maybe slightly, typically more than, slightly more than 2000, and definitely less than 3000, 4000, and one can expect by a few thousands of Reynolds numbers the flow to have become fully, the flow to have transitioned into 100% turbulent flow, not intermittently turbulent flow. And for pipe flow, we define Reynolds number as the average velocity times the inner diameter of the pipe divided by the kinematic viscosity of the fluid. If you consider the other simple case of boundary layer flow over a flat plate, then you define Reynolds number based on the free stream velocity, that is the approach velocity of the fluid onto the plate, and the length is defined as the distance from where the plate begins, where the flow of the plate begins. And so as the fluid is flowing over this plate, the Reynolds number continuously increases because the distance from the beginning of the plate increases. And at some Reynolds number, typically of the order of 500,000 to 1 million, there is a transition to turbulent flow, and you have the characteristic features of turbulent flow appear, and they become firmly established by about 1 million, Reynolds number of about 1 million. If you take the other simple case, another simple case of flow over a sphere, again it is a well characterized flow in the sense that you have a sphere in an infinite fluid medium. Sphere has a characteristic length scale, which is the diameter, and again we are looking at the approach velocity or the free stream velocity of the fluid as the characteristic velocity. So u infinity times d by nu is the Reynolds number in this particular case, and here the transition to turbulence happens at a Reynolds number of 200,000. Okay, so that's pretty high, although we don't expect it, and people expect this transition to be more like 50 or 100 or a few hundred, but around the Reynolds number of around 50 to 100, what we have transition is from a steady flow into an unsteady flow leading to vortex shedding is the transition that takes place around Reynolds number 50 to 100. So that vortex shedding type of flow exhibits some characteristics of turbulence, but it is not really turbulent flow. One would have to wait for or increase the velocity to a very high value such that Reynolds number goes up to about 100,000, 200,000 for turbulent flow over the sphere to set in. If you take other kinds of practical equipment like stirred tank reactors, where you have a vessel, cylindrical vessel, and you have an impeller which is rotating at a particular speed, then you define the Reynolds number based on the impeller tip speed and the diameter of the impeller divided by the viscosity of the fluid. in cases like this, it's not like a clear, geometrically clean flow. In the sense, impeller can be having quite a complicated shape, and it is not a 1D type of thing, it is a 3D, three-dimensional effects come in, and it is not a sustained, the flow does not have the same sustained character as in the case of for example pipe flow. Okay, so very close to the impeller you have a lot of turbulence, and far away from this you have little turbulence, but there is still the confining wall of the vessel that is pretty close. So it is not like flow over a flat plate where the physical dimensions of the fluid domain are infinite, and similarly flow over a sphere, again you have an isolated sphere in an infinitely long and wide medium. So for all these cases it is difficult to precisely say, okay, this is the Reynolds number beyond which you have transition to turbulence. Typically anywhere between 1000 and 20,000 can be a transitional regime, and beyond 20,000 or so one would expect the flow to have become fully turbulent. If you look at flow through porous medium, one would not imagine porous medium and the high pressure drops and all those things leading to turbulent flow, but if you have a Reynolds number of less than 10, one would say that it is laminar flow, and Reynolds number greater than 1000 is probably what is required for the flow to have become turbulent. And so the Reynolds number in this particular case includes the porosity as a variable in the Reynolds number definition. And on the other hand, as you go to very tiny channels, micro channels or compact heat exchangers with very small length scales, for example the gap between plates of a compact heat exchanger can be of the order of 1 or 2 millimeters. In such cases, even though these are like flow through ducts and pipes, you have a transition to turbulent flow which happens at much lower Reynolds numbers of the order of 500 to 1000. And here one should also keep in mind that in many of the cases here, when we talk about transition to turbulent flow, especially in the cases of pipe flow and channel flow type of situations, we are looking at the Reynolds number at which the linearity variation, okay, between linear variation between the pressure gradient and the characteristic velocity, that stops being linear, is considered as the Reynolds number at which turbulent flow transition to turbulent flow begins. So in that sense, it is not based on the usual characteristics that are exhibited by turbulent flow, as we will see. So when you say that the Reynolds number at which the velocity pressure gradient relation becomes stops being linear is the Reynolds number at which turbulent flow is supposed to have happened, is not such a clear definition of what turbulent flow is. Turbulent flow in the more rigorous sense is characterized by rapid and highly localized turbulent localized fluctuations in flow parameters such as velocity components, pressure, temperature, species, concentration. All the usual flow parameters exhibit rapid and highly localized turbulent fluctuations, and there is a characteristic signature of turbulent fluctuation that is present. When that characteristic signature is there, then we say yes, this is a turbulent flow. If that is not there, the mere fact that there is velocity fluctuation or the drag fluctuation does not make it turbulent flow. And the case in point is the flow over a sphere. At a Reynolds number of 100 for flow over a sphere, you begin to have vortex shedding, which induces a certain variation, okay, time dependent variation of velocities at different points within the flow close to the body, but still the flow is not turbulent. It becomes turbulent and it exhibits those turbulence like signature fluctuations only at a much higher Reynolds number of the order of 200,000. Okay, so that is a very important distinction between an unsteady flow and turbulent flow. So, turbulent flow is characterized by rapid and highly localized fluctuations. These fluctuations are generated in regions of high shear where you have strong velocity gradients are usually the locations where these are created, such as near a wall or in a mixing layer where again you have two fluids of different velocities are brought together. Okay. And in these regions of high shear there is an internal inherent instability mechanism that arises from these high velocity gradients, and that leads to the said characteristics of turbulent flow, which is rapid fluctuations and highly localized fluctuations. And these fluctuations are therefore generated by the flow itself, and these are sustained by the flow, and although these are instabilities, they never grow beyond a certain limit, and in that sense they are regulated by the flow itself, so that instability does not lead to breakdown of the flow. Okay, just like when we say you have an unstable bridge, then we expect those kind of images where the bridge starts oscillating very wildly and then at some point it breaks down. So, that kind of breakdown does not happen in this, it is just that it exhibits very rapid fluctuations, and these fluctuations will persist as long as the flow is maintained. That is, if you have a flow through a pipe going at a Reynolds number of say 100,000, then if you are able to measure the velocity fluctuations at a particular point, then those fluctuations never really die down. They persist as long as the Reynolds number is maintained at that 100,000. These are not externally generated, these are generated by the flow inside the pipe, and so you do not need an external impulse for these to be generated. The only thing that needs to be given so as to maintain these fluctuations is the driving force that needs to be maintained. In this particular case, the pressure gradient imposed on the flow needs to be maintained so that the flow is sustained at the Reynolds number of 100,000. Okay. So, there are some special characteristics of turbulent flow which are definitely very important for us when we are looking at fluid flow and the related phenomena. And one such thing is that the fluctuations that we are talking about of associated turbulence are pretty small. For example, typical amplitude of velocity fluctuations is in the range of 1 to 10% of the mean velocity. So, if you have a mean velocity of 1 meter per second, typically under turbulent flow conditions at a particular location, it may vary between 0.9 and 1.1. It is still very small compared to the overall velocity of 1 meter per second. But despite this being small, you have very important strong effects that are associated with turbulent flow. Okay, the features that we look for example, features like what is the pressure gradient, what is the friction factor, what is the heat transfer coefficient, what is the mass transfer coefficient, what is the reaction rate. These are the matters of interest to an engineer. Okay. Now, these things are strongly affected by these low amplitude fluctuations, these low amplitude very high frequency fluctuations. Okay. So, flow dependent quantities such as the pressure drop, heat transfer rate can vary by orders of magnitude. Okay. So, we will see that in the next lecture, but in this lecture we will just talk about it and then we will become more quantitative in the next lecture. Transport properties such as friction factor, heat and mass transfer coefficients and reaction rates can change by orders of magnitude compared to the value that would prevail if the flow remained laminar at the same Reynolds number. So, if you look at the pressure gradient or the friction factor in flow through a pipe at a Reynolds number of 100,000, and if you look at what it would have been if the flow were laminar, then the ratio of the two would be very high, of the order of 10 or 100, like that, depending on what kind of flow and at what Reynolds number you are talking about. In many cases, the enhancement or suppression in some rare cases, okay, for example, the drag on a sphere around transition numbers is something that decreases as you go from laminar flow to turbulent flow. That is a rare case, and we know why that is so, but typically otherwise we have an enhancement of the transport rates, transport coefficients, and this enhancement depends on the Reynolds number in a non-trivial way. Okay, it is not like a multiplicative factor of 10 or 50 or 100. That multiplicative factor value itself depends on the Reynolds number. It depends in a non-trivial way. For example, friction factor in laminar flow is proportional to 1 by Re. Okay, so that means it is proportional to Re to the power n, where n is minus 1. In turbulent flow, that proportional, the power factor n is minus 0.25, minus 0.2, it is much less, and so that means that the friction factor is going to be much higher in turbulent flow. And similarly, Nusselt number, which represents the heat transfer coefficient in a non-dimensional way through a pipe, in laminar flow it is a constant value, maybe 3.65 or 4.33 for the two cases of constant wall temperature and constant heat flux. It is only of the order of 3 to 4, but in turbulent flow it is proportional to Reynolds number to the power 0.8. So that means that if you have a Reynolds number of the order of 10 to the power 5, then the Nusselt number can be of the order of 200, and so that gives an enhancement of the factor of 50. So the Nusselt number, the heat transfer coefficient, is 50 times more than what you would have estimated if the flow were laminar, or if you neglected the effect of the fact of turbulent flow. And what does that mean? That means that in a typical heat transfer problem, you would like to estimate what is the heat transfer surface area. Okay. So, the surface area, if you have flow through a pipe, then it translates itself into the length of the pipe that is required. So, if you make a 50-fold increase in heat transfer coefficient, then the length of the pipe will be reduced by a factor of 50. It may not quite happen that way, because in a typical heat exchanger, the heat transfer coefficient on the inside and outside and through the pipe wall, all these things come into picture, but what it means is that your heat transfer equipment, the heat exchanger, can be too large for the duty that it is supposed to do. And similarly, if you underestimate the friction factor, assuming it to be laminar flow, then the pump that you require to maintain flow through a particular pipe at a particular Reynolds number can be small by an order of magnitude. You probably would have required a 10 horsepower pump, and you bought only 1 horsepower pump, because that is what you estimated. So, it can be like that. So, you can grossly over design or under design your heat transfer or fluid flow equipment if you neglect the fact of turbulent flow. Okay. So, this is including the effect of turbulent flow is very important in our design calculations. Okay. Now, there is a problem with that. The problem is shown in this figure. Okay. It is a typical variation. We mentioned that turbulent flow is characterized by rapid and highly localized fluctuations in flow parameters, and the squiggly variation that we are seeing here, where you have this can be it's a schematic. You have a velocity component which has an average value of 0.5, but it's not 0.5, it's changing wildly like this very rapidly, and on the time scale on the horizontal axis you have time, and although it is on the average steady, it is changing very rapidly, and something like this is the characteristic feature. If we were to neglect these fluctuations and then just take the average value to be 0.5 and keep it that way in our calculations, then we are going to grossly underpredict or overpredict our heat transfer coefficients and pressure drops. Okay. Now, if you want to take account of these fluctuations, you have a different problem. For example, in a case of flow through a pipe of a diameter of say 5 centimeters and at a Reynolds number of 100,000, which is not atypical, you have a velocity of 2 meters per second of water. So, water flowing through a pipe of 2 meters per second in a pipe of 5 centimeter diameter will have a Reynolds number of 100,000. So, for such kind of flow, the time axis here, which is given as 0 to 1 here, is such that the velocity fluctuations, we talk in terms of time scales of fluctuations. So, that is how rapidly it is changing. If you say like this, a sinusoidal variation, what is the time period of oscillation? So, that can be of the order of tens of milliseconds, okay. And the variations are not only with respect to time, they are also with respect to space. So, that means that the velocity at this point and the velocity at this point are going to be not the same, they are not going to be related in the same way. For example, if you have a velocity gradient like this, then this may be 2 meters per second, this may be 2.1 meter per second. But in turbulent flow, this will not remain 2 meters, this will not remain 2.1 meters, both are fluctuating rapidly like this. So, even if you bring it down to very close points, then again they can be fluctuating. So, the length scale over which you can see significant differences in velocities because of fluctuation are the length scales, typical length scales, and these can be fractions of a millimeter. So, if you want to resolve these variations over fractions of millimeters and tens of milliseconds, you need to have a delta x of the order of say 0.01 millimeters and delta t of the order of 0.001 second. So, that means that if you want to represent your 5 centimeter diameter with a delta x of 0.01, you can imagine you will have 50 millimeters, 5000 grid points only in the radial direction, okay, or 2500 grid points in the radial direction, and that makes it a very huge grid. You will have millions and millions of grid points, and you will have to run time dependent calculations over thousands and thousands of time steps. So, that will be humongously expensive to do computationally. So, this is the difficulty with the turbulent flows, and how we resolve this and how we overcome it through some modeling is what we are going to discuss in the next 3-4 lectures. Okay. Thank you.